Welcome everyone. Question number 101. Which of the structures of figure 12.28 will experience sway? First of all, we have to know what is sway of the structure. The lateral movement of a structure due to the lateral force is called sway of the structure. And this lateral force may be wind force, earthquake force, or any kind of horizontal loading. And few sway condition will be when the supports of the structure are not in same position, when the loading is eccentric on the structure, not at the middle of the structure. The member of the structure has non-uniform section, like one member has moment of inertia I, other member has moment of inertia 2I, when horizontal loading on the structure, as I said earlier. And last but not the least, when one of the supports of the structure settles with respect to others, then there can be sway for the structure. The portal frame or the structure shown in the option A, that is a frame subjected to a point load at the center, also subjected to a horizontal load at joint B. Just think, this load is absent, this horizontal load is absent, so the structure is symmetrical with respect to this load and with respect to this dimension. Okay, but if we consider this horizontal load, the structure will be unsymmetrical and there will be sway for this horizontal loading W2, and for the concentric load W1 there will be no sway for the structure, but the displacement will be there for the structure, and the displaced shape after the application of this two load will be like this. B will be B dash and C will be C dash after the application of the horizontal loading or the point load W1. So for this structure given in option A, there will be sway. Next, for the structure shown in option B, subjected to a point load W at the center. For this load, the structure is symmetrical. Okay, so the displaced shape for this structure after the application of this load will be this. Only vertical deflection of the member BC will exist, but there will be no lateral movement because there is no horizontal loading and supports are in same position of the structure. So only vertical movement is possible for this structure, so there will be no sway in this structure. Next, for this structure shown in option C, this structure subjected to a point load, but this load is at a distance L by 4 from the B, so this load is eccentric, not at the center of the structure, so the structure is not symmetrical with respect to with this load. So the displaced shape after the application of this load will be like this. Point B will go to B dash in this direction, left direction, because the load is at the left portion from the middle, and this point C will go to at this point C dash. Otherwise there will be no sway for the structure. The supports of the structure also in same position, so for only this eccentric load there will be sway for the structure. Now for the structure shown in option D, this is the same structure given at option C. Okay, but to prevent this sway, extra additional support is provided here at this point. This point is E. Okay, so there will be no sway for this structure. Option B is right answer. Question number 102. A symmetrical two-hinge parabolic arch when subjected to a uniformly distributed load on the entire horizontal span is subjected to only normal thrust. Option B is right answer. Question number 103. A two-span continuous beam ABC is simply supported at A and C and is continuous over the support B. Span AB is equal to 6 meter and BC is equal to 6 meter. The beam carries a UDL of 2 ton per meter over both these spans. EI is constant for the entire beam. The fixed end moment at B in span BA or BC would be. So this is our continuous beam ABC subjected to a uniformly distributed load 2 ton per meter. The total length of the beam ABC is equal to 12 meter, but span AB equal to 6 meter and span BC equal to also 6 meter. So under this UDL load for span AB, the shape of the bending moment diagram will be parabolic, and for span BC the shape of bending moment diagram will be also parabolic, and the ordinate or height of the parabolic will be WL square by 8 maximum bending moment, or here the ordinate will be same, WL square by 8. W means 2 ton per meter and L is the span of this of AB, that is equal to 6 meter, so WL square 8 will be equal to 9 ton meter, and same for this span BC, the ordinate value will be 9 ton per meter. This end A and end C is simply supported, so moment at A and moment at C will be 0, and we have to find out only the moment at B. So to find out the moment at B, we will use three moment equation, and this equation is MA L1 plus 2 into MB L1 plus L2 plus MC into L2 equal to minus within bracket 6A1 x1 by L1 plus 6A2 x2 by L2. L1 is the length of this span AB and L2 is the length of this span BC. So both will be equal to 6 meter, and A1 is the area of bending moment diagram for this span AB, and A2 is the area of the bending moment diagram for this span BC. So area of the bending moment diagram will be 2/3 base into height. So 2/3 A1 A2 will be equal to each other. So A1 A2 will be equal to 2/3 into base is the 6 meter for this span, and height is or ordinate is 9 ton meter. So we will get A1 A2 will be equal to 36 meter square, and x1 is the distance of CG of this bending moment diagram from the point A, and x2 is the distance between the center of this bending moment diagram from C. So both x1 will be x2 equal to each other, and it will be equal to 6 by 2 equal to 3 meter. Now putting all the value into this three moment equation, we will get MB, the value of moment at B, equal to minus 9 ton meter. Option B is right answer. Question number 104. A beam with a cantilevered arm BC supporting a freely supported end span CD is showing in the figure 12.29. Which one of the figure 12.30 represents the influence line diagram for shear force at A? So this is our beam ABCD. C is a internal hinge, and this hinge C allows free rotation between the beam segments. We have to find out the influence line diagram for shear force at A. Now let's assume the beam is subjected to a unit load at a distance x from A, and reaction at A is RA and reaction at B is RB. BC is the overhang portion and CD is another part of the beam. If we take moment at B, so summation of moment at B equal to 0. This reaction RA will be into L into distance L, and RA is trying to rotate in clockwise direction with respect to point B, minus this unit load trying to rotate in anti-clockwise direction with respect to point B, minus 1 into L minus X equal to 0. After the calculation, RA will be equal to L minus X by L, RB will be equal to X by L. To draw the influence line diagram for shear force at here, so X is equal to 0, so RA will be equal to 1. Now this line, the line will be connected to 0 at this point B, because at this point X will be equal to L. So if we put X equal to L at here, RA will be equal to 0. Now this line will be at C. Okay, as this is a internal hinge, so this member CD is flexible, so this member will also be connected to this member at point C. Now see, this ordinate is 1, and we have to find out the ordinate CQ. Suppose this ordinate is X. We got two similar triangle APB and BQC. Okay, so by these two similar triangle, we can equate this vertical length by horizontal length of this triangle APB equal to this vertical length X divided by this horizontal length XL by 4 in the triangle BQC. And after calculation, X will be equal to 0.25. Option A is right answer. Question number 105. The strain energy stored in a simply supported beam of span L and flexural rigidity EI due to a central concentrated load W is. Suppose this is a simply supported beam AB subjected to a central point load W. Now let's take a section X dash at a distance X from B. So this beam divided into two parts AC and BC. Now say reaction at this end A equal to RA and at this end B equal to RB, and that will be equal to W by 2, because RA will be equal to RB. Now we know the formula for strain energy equal to mx square dx by 2 EI. EI is the flexural rigidity and mx is the moment at a section X. So moment at X will be W by 2 into X, W by 2 into X. For this part of the beam, the strain energy will be the integrated value 0 to L by 2 into mx square, that means wx by 2 square into dx by 2 ei. And if we find out the total strain energy of the beam UAB, then this value will be multiplied by 2. Now if we calculate, we will get total strain energy of the beam equal to w square L cube by 96 ei. Option D is right answer. Question number 106. In a 2-hinge arch, an increase in temperature induces maximum bending moment at the crown. Option C is right answer, as horizontal thrust is proportional to rise of the temperature. Number 107. The following methods are used for structural analysis. Macaulay's method is primarily used for determining the slope and deflection of the determinate beams. Next, Coronal analogy method. This method is used to analyze the indeterminate structures, particularly rigid frames and continuous beams. Carney's method used for the analysis of the indeterminate frames as well. And method of section. This method is used to find out the internal forces such as axial force, shear forces, and bending moment in the determinate trusses and frames. So for structural analysis of only column analogy method and Carney's method is used. Option C is right answer. Question number 108. Figure 12.31 shows a frame to be analyzed by moment distribution method. The distribution factor for member GF, GH and GD will be respectively. Now to find out the distribution factor of these members, we have to calculate first the stiffness for these members. Now stiffness for member GF equal to 4ei by L. Now stiffness for member GH is equal to also 4ei by L, and stiffness for member GD is equal to 4ei by L. Here I is 2i and L is 2L, length of the member. That will also be equal to 4ei by L. The stiffness for all the member is 4ei by L because internal all the joints considered as fixed joint. So summation of stiffness K will be equal to 12ei by L. Now to find out the distribution factor for a member, we know the formula is stiffness of a member by total stiffness of all the member connecting at that point. So distribution factor for the member GF will be equal to 4ei by L by 12ei by L equal to 1/3, as the stiffness value for member GH GD is same as GF. So distribution factor for member GD and GH will also be equal to 1/3. Option B is right answer. Question number 109. The frame shown in the figure 12.32 has at this support the number of reaction component will be 3, and at this fixed end supports the number of reaction components will be 3. So 3 plus 3 equal to 6 unknown reaction components, and the 3 unknown reaction components at each end will be 1 horizontal reaction, 1 vertical reaction and 1 moment. So 3 at this end and 3 at this end, total 6. Option D is right answer. Question number 110. The absolute maximum bending moment in a simply supported beam of span 20 meter due to a moving UDL of 4 ton per meter spanning over 5 meter is. This is our simply supported beam AB of span 20 meter and subjected to a moving UDL 4 ton per meter for a length of 5 meter. Suppose we want to get the maximum bending moment or absolute bending moment in the center of the beam. To get maximum bending moment or absolute moment at a position of the beam under this load, we have to get the center of the UDL to the center of the beam AB. Let's find out the reaction at A and at B. So RA RB will be equal to this load 4 into total span 5 meter divided by 2 equal to 10 ton. So reaction will be 10 ton at each end of the beam. Now we have to find out the maximum bending moment at C, which is the midpoint of the beam. Bending moment at point C will be RB into 20 by 2 minus 4 into 2.5, half of the UDL span, into 2.5 by 2, because we have to take the half of the UDL span because UDL always acts at the middle. So after calculation, bending moment at C will be 87.5 ton meter. Option D is right answer. Question number 111. The influence line for horizontal thrust of a 2-hinge parabolic arch of span L and rise H will be as shown in. Option B is right answer. And for 3-hinge parabolic arch, the influence line diagram will be given at option A, L by 4H, that is the ordinate, and ordinate of this diagram is 25 L by 128 H. Question number 112. Force in the member BC of the truss shown in the figure 12.34 is. look, this is a triangular truss, so this angle is 60 degree and this angle is 60 degree. As this is a triangular truss, so this angle B will also be 60 degree, because we know by the property of triangle, the sum of all the angle in a triangle should be 180 degree. So this angle will be 60 degree as well. So we can say this triangular truss is a equilateral triangular truss. Okay, so the length of the member AC is 6 meter, length of the AB will be 6 meter, length of the member BC will also be 6 meter, and the height of the triangular truss from base AC to B will be root 3 by 2 into 6. The free body diagram of this triangular truss is like this. This angle 60 degree, this angle 60 degree, and this angle is also 60 degree, and we will determine the reaction at both end A and C under this horizontal load. So suppose reaction at this end is RA and at this end is RC, and the support at end A is hinge support and support at C is roller support. So there will be two reaction at this end, one horizontal reaction and one vertical reaction, and as this is a roller end C, so there will be one reaction component and that will be RC, vertical reaction. Now if we take moment at a point A, then the moment at A will be RC into 6, and RC is trying to rotate in anti-clockwise direction with respect to point A, so minus RC into 6, and this load is trying to rotate in clockwise direction with respect to point A, so plus 5 into this height from here to this height, root 3 by 2 into 6, the base length, equal to 0. Now after calculation, RC will be equal to 5 root 3 by 2. So at joint C, this angle is 60 degree, and say force at the member BC is FBC, and we also know the reaction at C will be, vertical reaction at C will be 5 root 3 by 2 as we calculated earlier. So by equilibrium for all the forces in vertical direction is equal to 0, we can write FBC sin 60 degree is equal to 5 root 3 by 2. And after calculation, FBC will be equal to 5 ton, and it will be compressive because the forces in the member BC is trying to go towards the joint C, so the force will be compressive. Option D is right answer. Question number 113. In respect of the beam and the given loading shown in the figure 12.35, match list 1 where span fixed end moments given with list 2 where value is given, and select the correct answer using the codes given below. So beam A, B, C, D is a continuous beam, and the intermediate support B, C will act as fixed support, as B will act as fixed support. So AB is a for this portion AB is a fixed beam, so fixed end moment at A will be minus WL square by 12, and fixed end moment at B will be plus WL square by 12. So MB equal to minus MA equal to WL square by 12, and L is the 6 meter span and W is the 4 ton per meter. After calculation, this value will be 12 ton meter. Next, span BC, this end, this support and this support is also fixed support because they are intermediate support, will act as fixed support. Okay, so now for this beam BC, the moment at B will be minus WL square by 12 plus WAB into A plus B by L square. WL square by 12, where W is 1 ton per meter, and WAB into A plus B by L square, here W is equal to 4 ton, and moment at C will be plus WL square by 12 plus WAB into A plus B by L square. A and B is written here, denoted in this figure. So MC will be equal to minus MB, the formula will be WL square by 12 plus WAB into A plus B by L square. The L will be span will be total 12 meter. Fixed moment at C equal to minus MB will be equal to 21 ton meter. Next the bending moment, the fixed moment at C will be minus WAB square by L square. A is this portion and B is this portion, so and L is total 6 plus 3 equal to 9 meter. So MC will be equal to minus 6.67 ton meter, and moment, fixed moment at D will be equal to plus WA square B by L square. A will be equal to 6 meter, A is 6 meter, B equal to 3 meter, and L is equal to 9 meter, so MD will be equal to 13.30 ton meter. Then D is right answer. Question number 114. The slope deflection equation of the member BC of the frame shown in the figure 12.36 is given by. We have to generate the slope deflection equation for the member BC subjected to a loading 15 kN per meter. So fixed end moment, so slope deflection equation for the member BC will be MBC is equal to fixed end moment at end B. So MFBC, FBC is the MFBC is the fixed end moment at end B plus 2 EI by L into 2 theta B plus theta C minus 3 del L, 3 del by L. L is the length of the member BC. Theta C is the rotation. Theta C is the rotation at end C. Theta B is the rotation at end B. And EI is the flexural rigidity of the member, and L is the length of the member BC. We know all the value. L equal to 8 meter, span of member BC, and the deflection at end B is nil. So 3 del by L, this term will be equal to 0, and fixed end moment at the end B will be equal to minus WL square by 12. W will be equal to 15 kN per meter, and L will be equal to 8 meter, the span. So after putting all the value, we will get MBC is equal to 0.25 EI into 2 theta B plus theta C minus 80. Option A is right answer. Question number 115. Which one of the following represents the correct influence line for bending moment at point C for the beam shown in the figure 12.37? So question number 115, this is a overhanging beam with overhang span BD and simply supported at ends A and at end B. Now say at a point C, unit load is acting from at a distance 3 meter from A and at a distance 6 meter from B. Now the bending moment at point C will be WAB by L. W is equal to 1 unit and A is equal to 3 meter and B equal to 6 meter, and L will be equal to 9 meter. So the bending moment value at point C will be 2 unit. Now moment at here at A is equal to 0, at B is equal to 0 because A and B is simply supported ends. Okay, but at D there will be some moment because the moment at D will be generated by the reaction at this end B into this length 2 meter. So reaction at end A will be W B by L, and reaction at end B will be W A by L. So the moment at D will be reaction at B RB equal to W A by L into 2. So the moment value will be 0.67. This diagram is negative due to load, and this diagram due to the reaction component is positive. Now as per this solution, the option is not given in books. Now if we divide this ordinate by 2 and this ordinate by 2, then option D is right answer. Question number 116. Consider the following statements with respect to arches. Statement 1. Normal thrust at any section of the arch is the component of the interacting forces on the section along the tangent to the center line of the arch. Statement 2. The radial shear at any section of the arch is the component of the interacting forces on the section along the normal to the center line of the arch. Statement 3. The intercept between a given arch and the linear arch at a section is proportional to the bending moment at the section. The arch which has funicular polygonal shape after the application of series of load over the arch is called linear arch, like the arch at the top given at the top, and the arch which is parabolic, circular or elliptical in shape and can be easily constructed is called actual arch or given arch. Now let's compare these two arch and let's take a section at this point of this linear arch and the given arch. Okay, and from the point to the base of the arch the height is y, and from this point to the base of the arch the height is y1. So y minus y1 is the intercept or the difference between the two arches at that point. So bending moment by the linear arch at the section xx will be this horizontal thrust h into y, and at this point by the general arch or given arch by the given arch the bending moment will be at this point h into y1. So net bending moment between these two sections will be h into y minus y1, and we can say bending moment is proportional to y minus y1, and that is the intercept or difference in height. All the statements are correct. Option A is right answer. Question number 117. A symmetrical parabolic arch of span 20 meter and rise 5 meter is hinged at the springings. It supports a uniformly distributed load of 2 ton per meter run of this span. The horizontal thrust in turn at each of the springing is. The parabolic arch is hinged at the top. So this is a three hinge parabolic arch. Height of the arch is 5 meters, span of the arch is 20 meters, and the UDL load subjected to UDL load, that is 2 ton per meter. The formula to find out the horizontal thrust at each end of this parabolic arch will be WL square by 8H. W is 2 ton per meter, L is the 20 meter, L is equal to span equal to 20 meter, and H is the rise of the arch is 5 meter. So after putting all the value in this, we will get the value of horizontal thrust H equal to 20 ton. Option C is right answer. Question number 118. A beam AB is fixed at both ends and carries a uniformly distributed load of intensity P per unit length run over its entire length. Due to some constructional defects, the end B is now reduced to a simply support. The percentage increase in bending moment at A is. Question number 118. For first case 1, the beam is fixed beam subjected to uniformly distributed load W per meter. So the bending moment at the end A will be MA equal to WL square by 12. Now due to constructional error, this B end is reduced to a simply supported ends. So for case 2, the beam is subjected to same kind of loading W per meter, but the moment at this end MA will be WL square by 8. So increase of moment at this end will be WL square by 8 minus WL square by 12 divided by WL square by 12 into 100% equal to 50%. B is right answer. Question number 119. Match list 1 with list 2 and select the correct answer using the codes given below. List 1, the structures are given, and in list 2, degree of static indeterminacy value is given. For this plane frame, the formula for degree of static indeterminacy will be 3m plus r minus 3j. M is the number of member, r is the number of reaction components at each end, and j is the number of joints. So m will be equal to 1, r, the reaction component will be 3 at this end and 3 at this end, and number of joints will be 1, 1, 2. 3 reaction components at this end will be 1 vertical reaction, 1 horizontal reaction, and 1 moment. And also there will be 3 reaction components at this end. So after putting all the value in this equation, ds will be equal to 3. For the beam given at option B, the degree of static indeterminacy formula will be same, 3m plus r minus 3j minus r dash, because of this internal hinge. R dash is the additional required, and the formula for r dash will be n minus 1. N is the number of member connected for the hinges. So there will be 2 member connected for the hinges. So number of member will be 1, 2, 3, 4, and number of reaction component will be 3 at this fixed end, and 2 at this end, 2 at this end, and 2 at this end. 2 at this end because one horizontal reaction, one vertical reaction, there will be no moment. And same at here, same at here. And number of joint will be 1, 2, 3, 4, 5. So after putting all the value in this equation, we will get ds equal to 2. Now the frame given at option C. For this frame, the degree of static indeterminacy formula will be same, but the number of member will be 1, 2, 3, 4, 5. Number of reaction components will be 3 at this fixed end, and 2 for this hinge connection, and 2 for this hinge connection. So 3 plus 2 plus 2 equal to 7, and number of joint will be 1, 2, 3, 4, 5, 6. So after putting all the value in this equation, ds will be equal to 4. Now the frame given at option D, the formula for ds will be 3m plus r minus 3j, same as earlier, but the number of member will be 1, 2, 3, 4, 5, 6, 7, and number of reaction component will be 3 at this end, 3 at this end, and 3 at this end. So total 9, and number of joints will be 1, 2, 3, 4, 5, 6, 7, 8. Now after putting all the value in this equation, ds will be equal to 6. Option D is right answer. Question number 120. A fixed beam AB is subjected to a triangular load varying from 0 at end A and to W per unit length at the end B. The ratio of fixed end moment at B to A will be. So suppose this is our fixed beam subjected to a triangular load 0 at this end A and W per unit length at this end B. So fixed end moment at the end A will be WL square by 30, and fixed end moment at this end B will be WL square by 20. And if we make the ratio between the fixed end moment B to A, the ratio will be 3 by 2. Option D is right answer.